Hello everyone. In previous lecture we have talked about nomenclature of alkyl halide and we see what are the different common or trivial names which can be assigned to the alkyl halides. So in today's lecture we will talk about some of the structural feature of alkyl halides and mainly discussing the physical properties of alkyl halides. So, in physical properties, when we talk about firstly, the very first thing is the polarity, which we haven't observed in the hydrocarbons. So, if you compare the hydrocarbons versus alkyl halides, so you can see that in hydrocarbons, as you know, that this bonding is only between the carbon, and the carbon hydrogen. But in case of the alkyl halide, there is the X, which is in a generic form, is mentioning the halogen attached to the carbon. So that includes the elements from the seventh group in the periodic table, which is called the halogen, fluorine, chlorine, bromine, and iodine, and these are basically the highly electronegative elements in the periodic table. So once they are attached with the carbon skeleton, so it means they are creating some of the charge or the dipole in in the molecule. So being the electronegative, they have the strong electronegativity to attract that electron density towards itself and making that carbon partially positive one. And of course that negative and positive charge is inducing along the rest of the structural chain. So this is creating the dipole moment, and we know the dipole moment is basically depending on the magnitude of the charge on the bonded elements or the atoms, and then their separation, that what is the distance between these one. So this picture is basically the electrostatic potential map of fluoromethane. So if you know about the fluorine, so this is very smaller in size as compared to the chlorine, bromine, and iodine, which, and at the iodine level, you know that this is quite bigger in the size. So fluorine is very smaller, just comparable as in some of the property like the hydrogen in its size, though it is bigger than the hydrogen one, but it is a very tiny element in the halogen one. So now in this electrostatic potential map, you can see this blue, which is the high energy, and this red, which is of the low energy. And there is the full saturation. So this saturation is making that there is the very significant charge separation among these molecules, and that will be when there is the significant positive and significant negative charge, and that is creating the dipole moment. So that dipole moment is basically responsible for the alkyl halides to make these the polar molecule. So here in this slide, you can see the table, which is giving the dipole moment of the halomethane, their values, in comparison to their electronegativity of halogen, which is the X element, which has replaced with the hydrogen in the hydrocarbon. And then there is the carbon halogen bond length in the picometer. So the dipole moment in the base D is giving its value. And now we can see, as we state, that the dipole moment is dependent on the electronegativity or the charge, magnitude of the charge on these participating elements, and then the bond length. So if you look at this halomethane, so from the fluoromethane and chloromethane, bromomethane, and iodomethane, so you can see the highest electronegativity is of fluorine, then chlorine, then there is bromine, and the iodine is having the 2.5, which is just equivalent, very negligible difference with the carbon, which has the 2.2 or 2.5, right? So you can see that this is electronegativity difference, and the electronegativity is decreasing down the group in the periodic table, and the fluorine is the highly electronegative element in the halogen one. But if you just compare the carbon halogen bond length, so the highest bond length, or the basically the gap between these two atoms which are bonded one, the carbon and the iodine, is the 214, that bond distance, and then there is 193, 178, and 139. So if you just look at this electronegativity pattern, so the dipole moment should straightforwardly increase on in the above direction. So for example, this is the 1.85 and this is the 1.62. So that makes sense because this is the highly electronegative and this is the as comparatively or relatively smaller, low in electronegativity values. So when you see the bond length, so the bond length of the fluorine is just 139 as compared to the 214, which is for the iodine, because iodine is a bigger in size. So there is more gap between the carbon and the iodine bond length. So then it these both factors are basically counter to each other, so they are deciding the dipole moment. So this is not straightly increasing or decreasing because these both factors, the electronegativity and the bond length, are count balancing each other wherever there is a difference. So the highest dipole moment is of the chloromethane, which has the larger dipole moment, right? And you can see that one. So that you can say that if you compare the chlorobromo and the iodomethane, so the chloromethane has the highest dipole moment in these elements. Now going to the next one. So this is just to refresh that what you know about the formula of how you can calculate the dipole moment. So I have told you that this depends on the size of the partial charges, the distance between them, and the polarizability of the three pairs of unshared electrons on each halogen. Now the next property is the boiling point. So for the boiling point, you again need to know that most of the haloalkanes are present in the liquid state. And this is because these are the polar molecules and they have the attractive dipole induced dipole, and induced dipole dispersion forces, and collectively they are named as the van der Waal forces, the attractive forces, which are making some of the compound the charge, and wherever there is enhanced electrostatic interactions, so they are raising the boiling point of the molecule. So that's why if you compare to the hydrocarbons versus the alkyl halides, so they have the higher boiling point. And if we compare within these halogens, and fluorine, chlorine, bromine, and then there is a methylene, and there is a methyl, and there's the iodo, and there's a hydrogen. So this is the van der Waal radii for selected atoms and the group of atoms. So van der Waal radii is basically the minimum radius or the distance between the which is for the linking or the attraction of the molecule, and this is not creating the strain in a molecule. So this is a distance where the attractive forces are overcoming the repulsive forces. So as they are closer and there is the attractive forces are overcoming by repulsive forces, so they are making these more polar, more electrostatically charged elements, and so there is enhancement or there is an increase in the boiling point. Now, for your understanding, so here we can see the examples. So one is the 1-bromobutane, another one is the 2-bromo-2-methylpropane. So this first case is basically the comparison between the linear and a branch structure. So here the same thing applies as we have seen in the hydrocarbons, that when we are comparing the hydrocarbon, which is a linear unbranched, so it has the more higher boiling point as compared to the branch. And the reason is this, because in a branch they have the more spherical, more close interaction, and the molecule is have the very has a very segregated, or you can say the low surface area, and this is in a spherical in a shape, so that decrease its boiling point. So that's why the 1-bromobutane, and in comparison to its competitive structure, which has the 2-methyl propane, and there's a 2-bromo, so the 2-bromo has a 72 Celsius, and while the 1-bromobutane has a boiling point 100 degrees C. So now the next thing is when you compare the hydrocarbon versus the alkyl halide, so we can also compare the magnitude of the difference, that how drastic change has appear when you shift from the hydrocarbons where all bonds are the carbon and hydrogen. So there is no strong electronegativity difference between the carbon and hydrogen bonding, or a carbon carbon bonding, which are of the same atoms. So when you go for these bromomethanes or the alkyl halides, so here you can see the ethane, and in its comparable structure, bromomethane. So what is the difference between the boiling points? So ethane boiling point is minus 89 Celsius, and the bromomethane is having the 4 degrees C. Now, the third is the density. So, the density of liquid haloalkanes are greater than those of hydrocarbons of comparable molecular weight because of the halogen's large mass to volume ratio. Because we know the density is m over v, and the mass over volume, if that ratio is higher, so it means they are more have the high density as compared to the other hydrocarbons. And if we can take into account the water molecule, so a bromine atom and a methyl group have almost identical van der Waals radii, but bromine has a mass of 79.9 atomic mass unit. So compare with just a very smaller number for the methyl, which is just a 15. So the density of all liquid bromoalkanes and iodoalkanes are greater than that of water, because we know that its water density is 1. And when there is a bromo and iodo, which are the bigger elements with bigger halogen atoms, and they have the high mass, so of course that is making their higher ratio of mass to volume and having the greater density value. So they are denser than the water. Although the density of liquid chloroalkanes are less than that of water, but further substitution of chlorine beyond the one, so if we have the more than one halogen, more than one chlorine with the molecule with the hydrocarbon, so then they are giving the high density, because now this chlorine weight is added, and this is again increasing the mass to volume ratio of that chloro alkanes. So then again that will be denser than the water. So the densities of some low molecular weight haloalkanes are there for your information, and you can just refer to that table. So you can see that almost all of the bromo and the iodo have the higher density than the water. But if you just look at these chloro one, so in chloro, that will increase once we are replacing the more than one hydrogen with the chlorine. But this example is just with one substitution of the replacement of the one hydrogen with the chlorine, bromine, or iodine. So this is methyl, ethyl, propyl, isopropyl, butyl, and tertiary butyl. So here we have just replaced the one hydrogen with the halogen one. But if we so straightforwardly for the bromine and iodine case, if there is the bromo alkane or iodoalkane, so they have the more density than the water. And in case of the chlorine, when you will move from the monochloro alkane to the di or the tri one, so they are more denser than the water molecule. So then density of the polymethane is just to make you this fraction visible, or this number or this difference visible, that you can see that if this carbon which has replaced with the two halogen, so you can see the density values, so they all are greater than the water. Then if that is replaced with the three halogens, again that is greater than one, and there is huge increase in the density one. And then if that is fully replaced with the halogen one, so now you can compare the values of these one, right? Now at the end there is the checkpoint quiz to see that either you get that in idea that what is the density has impact when you're conducting some of the solvent extraction. So solvent extraction is basically a physical method of separation of two immiscible solvents, and to get your product, if your product is either soluble in a water medium or soluble in a organic solvent. So in the aqueous and organic solvent, so you can easily separate these, or even two other immiscible organic solvents, so you can separate these two layers, and you can get whatever wherever the product you have in which solvent system. So now I have given you this case, that this is the solvent extraction flask, right? And there is the grayish layer and there is the transparent layer. So these are the two layers, and I have provided you the two immiscible solvents, and these two immiscible solvents are, the one is the water and the chloroform. So you just have to label on the basis of the density, so which is the upper layer and which one is in the lower layer. So you have to think about that either the water is having the high density versus the chloroform, or the chloroform has the high density than the water. So just label that one, and you can share that sheet on the Moodle, that you can just answer that one, that what is your quick answer for that checkpoint quiz, that either you are able to see that what will be the difference and which is the denser among these water and a chloroform mixture of the two immiscible solvents. Okay, so that's for the physical properties, and in the next lecture we'll talk about the chemistry of alkyl halides and their reactions and their synthesis. So have a good day. Thank you.